in all of the work we have done so far. Here's a function. Take a derivative. Take a second derivative. Interpret those derivatives. Let's work from our function to our derivatives. What if I go the other way? So if I think of a practical example, I have a speed, my velocity at given points in time. I can track that. I have a speedometer. If I have that speedometer, how do I get distance, position from it? How many of you saw the movie Hunt for Red October? Do you remember they are in a submarine driving, running through this strait, trying to navigate it, and the only way they have to do it is a map and a stopwatch. Because I know which way I'm going, how fast I'm going, where am I? I have to recover position information from speed. So I could tell you something about f prime and ask you, what does it tell me about f? This is the reverse of what I just gave back to you on the homework. An antiderivative for a given function. So capital F is an antiderivative of little f. If when I take the derivative of capital F, I get little f. An example. If I tell you I have the function 3x squared, what is 3x squared the derivative of? Aha. There we go. However, I need you to go back to chapter 4, section 2, the mean value theorem. At the very end of our discussion of the mean value theorem, I wrote down two statements. There were consequences of the mean value theorem, and I put a star around one of them, and I said, this is going to come back and be important. What did you write down? Very last two things I said when we did Rolle's theorem and the mean value theorem. Jack?
If the derivative is equal to 0, and then if you live in constant.
Okay, so if the derivative is 0, then the function it came from must be a constant, and then the next one.
If derivative, if f of x, f prime of x equals g prime of x on that point, and f of x minus g of x equals c.
So if I have two things that have the same derivative, then the difference between the two original functions is a constant. Hey, wait a minute. I need to be sneaky up here. The sentence I said about antiderivative, right here. F of x is an antiderivative, not the antiderivative. That means there's more than one. But if I had two different functions whose derivative was 3x squared, then the difference between those two functions must be a constant. So any other antiderivative of 3x squared is only different from this by a constant. Every single antiderivative of 3x squared is going to look like x cubed. Except there might be a number on the end. Because if you take the derivative of 7, what's the derivative of 7?
0.
The derivative of 15, derivative of square root of pi over 3, they're all 0. So they don't contribute anything to the derivative. And that means I could think about generalizing this idea. As long as I make the statement that that capital C represents some constant, I don't know what constant, but some constant, then that expression, x cubed plus c, encompasses all possible antiderivatives for 3x squared. I'm going to call that the general antiderivative. And in general, anytime I take an antiderivative, unless I specifically need to know the value of the constant, I'm just going to put plus c on the end and say, hey, some constant can go here. It could be 0, it could be 113, it could be negative 73. I don't care. There'll be some number. Geometrically, if I asked you to graph all three of these and the original function x cubed, what would you see in those graphs? Okay, you waved your hands or you said shift. Where's that shift occur? Vertically, right? Because adding a number on the end of the function moves it up. Subtracting one moves it down, but they're all parallel. We think of parallel lines as having the same slope. These curves are parallel because their slope is the same everywhere. Their slope is 3x squared. At any given point, they have the same slope. Page 357, you'd see something like this. It's all the same curve, it's just moved up or down by whatever the appropriate c is. Okay. So how do I take and find antiderivatives. Major advantage. All I have to do is work the rules I already know in reverse. That's why, way up here, I said, let's go backwards. I just wrote it backwards to be silly about it. Here are a handful of functions. Sine of x, e to the x, 1 over 1 plus x squared, 1 over x. I like antiderivatives for all of these. Advantage. All of these functions are derivatives of things we already know. All I have to do is figure out what that is. All right. Something whose derivative is sine of x. Grab your last exam. There was that formula sheet on the back of it with all the trig functions, right? It's on the exam review sheet as well. So if you've got Canvas open, you can look it up there. We have a list. I don't have to have these memorized. I'm very happy about that. I am assuming, though, that you left the formula sheet attached to your exam. If you tore it off, you don't have it. So you might need to look it up on Canvas. Or you might go back to the beginning of chapter 4 in our notes, in our textbook, where we wrote that big list. Okay, hang on a second. Trig functions. Say again?
Negative cosine.
Deriv sine is cosine, deriv cosine is negative sine. I got to move the minus sign around, so I put the minus on the cosine. But wait, there's more. Yes, our chain rule comment comes back. What has to go on the end of this? To make a general antiderivative, I need a constant here. I don't know what constant it's going to be. It could be anything, so I'm going to put that plus c every time. What's something whose derivative is e to the x? Yay! So the antiderivative of e to the x is e to the x plus some constant. 1 over 1 plus x squared. Wait a minute, that looks like it should be quotient rule, but I get to cheat. Because this one actually doesn't come from quotient rule. This one comes from my inverse trig functions. This expression is the derivative of the inverse tangent. This is a matter of pattern recognition. And actually taking the antiderivative without knowing that that's part of my inverse trig functions is a major pain in the ass. So I really need to have that, oh, that is one of the special ones on my formula sheet. The other one we end up using a lot is the inverse sine. Which is the one over the square root of 1 minus x squared. Those two will be the most commonly used inverse trig antiderivatives. But again, I have a formula sheet, so it pays to remember those. Are on there. 1 over x. What's something whose derivative is 1 over x? Almost. ln of x only works when x is positive, right? But 1 over x also works when x is negative. If I really want my function to cover all of the same domain, I need something that works on both sides. But I can only put positive stuff into an ln. We cheated when we were talking about the derivatives of ln back in chapter 3. We used an absolute value. So if I actually want to use ln of x, I need the absolute value of x to account for the fact that I'm allowed to use negatives. Wait a minute. When I did 3x squared, I got x cubed, right? The antiderivative of 3, but there's no 3 this time. How do I deal with the fact that there's no 3? When you take the derivative of x cubed, what's the formula for taking that derivative tell you to do? Our power rule.
Multiply by the power of the exponents, 10 minus 1.
So I subtract 1 from the power, I multiply, well, first I multiply by the power, and then I subtract 1. My goal is to go backwards, right? So let's do those steps in reverse order. The last thing I did was subtract 1 from the power. So the first thing I'm going to do is add 1 to the power. I multiply by the power I brought down. So what's the opposite of multiply? I'm going to divide. I'm going to divide by the new power we just came up with. Notice what happens. If I go to take the derivative of this, the 3 will cancel with the 1/3. That'll give me the 1 that's in front here, won't it? Oh, you sneaky person, you. I can generalize this. Any power, x to the nth. If I do the antiderivative of this, let's follow that backwards idea. I'm going to add 1 to the power, and I'm going to divide by the new power. You'll often see this written as x to the n plus 1 over n plus 1, rather than with a 1 over n plus 1 out in front. Those mean the same thing. You can write it either way. Question. What power is going to up that up? What value of n is going to make that go? -1, right? But that would mean that we'd had x to the -1 here, right? But x to the -1 is up here. So we can really do any power of x you want. This rule works as long as the power is not -1, but this rule works for -1. I have a power rule for antiderivatives, just like I had a power rule for derivatives. Huh. Questions? Talk to me. We had a bunch of other rules for taking derivatives, right? If I added things, I took the derivative of each one. If I subtracted things, I just took the derivative of each one. Those rules carry over here as well. If I multiply by a number before I take a derivative, I just take the derivative and then multiply by the number. I can do all those same things here. So if I ask, hey, here's a function, f prime of x is 4 sine of x plus 2x to the fifth minus root x all over x. And I ask you, what's the function this came from? You can do this just using the rules we currently have. But I see that confused look on your head. You're looking at that last piece going, what the, right?
What does it say?
2x to the fifth minus root x over x, or the thing under it?
No, that was.
Okay. This last piece is division. The quotient rule was hard. So working the quotient rule is going to be difficult. But this is a fraction with a simple denominator and a compound numerator. So it's actually easiest if we split that fraction up. So I'm going to rewrite this part. As two separate pieces. 2x to the fifth over x minus square root of x over x. Simplify those last two pieces. What happens here?
is equal to
And I'm going to get
2x is 4.
perfect. That's something that I can use the power rule on. What about this last term? Because there's a 1 in the bottom and a 1/2 on top. That is a perfectly valid power of x. I can use x to the n power rule. So now I can tell you what f of x looks like. I can start taking antiderivatives because this is now all in forms that I know antiderivatives of. What is the antiderivative of 4 sine x? Exactly. -4 cosine of x. The 4 stays there. It's just being multiplied on. The antiderivative of 2x to the fourth. Well, we'll just leave the 2 there for the moment. What's the antiderivative of x to the fourth? Two times 1/5 will give me 2/5. So I can write it like that as one step. What about the x to the -1/2?
One over 1/2 x to the 1.
That is exactly what it is. Well, what's 1 over 1/2? Rip it out of the bottom, flip it over, you get 2. And a 1/2 power is a... So I could write this. Now I want you to understand, my first calculus teacher, Senora Maria Soto, I went to high school in Miami. She was from the University of Havana. She was this tall and built like a barrel, and this woman, I had her at 7:30 in the morning. You think I'm crazy at 9 o'clock? Imagine this at 7:30. I lost 2 points for this. This answer, I got -2. What did I do wrong? Twice. Here comes my infomercial voice. But wait, there's more. Every single line, once I do an antiderivative, must have the plus c on it. If you only put it on the last line, you'd lose a point on every place you forgot it. My first homework paper on antiderivatives, I earned a negative score. I will never forget this damn plus c ever again. And I hope you don't either. Questions? You have just solved for me what is commonly referred to as a differential equation. Any equation that involves derivatives of a function is a differential equation. We've seen at least one other kind of differential equation already. The differential equation when we did population growth. The equation we had was dy dt is proportional to y. That's a differential equation because it involves the derivative of y, and it also involves y itself. This was a differential equation because I gave you f prime and you gave me f. So we started with the derivative, we ended with the function. Here I start with an equation involving my derivative, and I end up with the function. There is an entire course on differential equations, the basics of which we will see in chapter 9 next semester if you're taking Calc 2. But the techniques for differential equations are used everywhere. Engineering, physics, chemistry, biology, social sciences, communication, computer science, they're everywhere. So I like being able to solve differential equations. When we did our population problems, our temperature problems, we had additional information. If I have that extra information, I call those initial conditions or boundary conditions. Initial conditions all happen at the same x value. Boundary conditions can happen at different x values. We'll talk about that more next semester. But the overarching goal is that if I start with information, I can then figure out the value of C. Back here, we were figuring out the value of A, we were figuring out the value of K, weren't we? We had that extra information, we used it to solve for the constants. Here's an example. F prime of x is e to the x plus 20 x squared plus 1 all to the negative 1, and f of 0 is negative 2. This extra bit of information, that's my initial condition. That's going to allow me to go from a general antiderivative to a particular antiderivative. Questions? Let's solve this. What's the antiderivative? What is f of x here? The e to the x part's easy. It's the other part, isn't it? So what the hell do I do with that?
You're going to make the one on X.
Careful, it wouldn't be 1 on x. It would be 1 on that whole thing, wouldn't it?
Yeah.
So I would write this as f prime is e to the x plus 20 times 1 over x squared plus 1. Hey, wait a second. I've seen that before. Only I wrote it as 1 over 1 plus x squared, didn't I? So it doesn't matter. I'm adding. It doesn't matter what order that is. I know that. What's the antiderivative of that thing? The inverse tangent. So f of x is e to the x plus 20 tangent inverse of x plus c. This is my general antiderivative. And here's where I get to use my initial condition. That initial condition says if you plug in 0, you're going to get out -2. Oh. F of 0 equals -2 means -2 is equal to e to the 0 plus 20 tangent inverse of 0 plus c. What's e to the 0? What's tangent inverse of 0? You have a calculator with a tangent inverse button. Yay! 20 times 0. So this right-hand side is c plus 1. And that means that c is equal to -3. And that means that I now have a particular antiderivative. F of x is e to the x plus 20 inverse tangent of x minus 3. If we go back and think of that giant collection of parallel curves, we pick the one that goes to the point 0, -2. So instead of having all of these options, this initial condition said pick that one. And that's what this is referred to. This is the particular antiderivative. Based on our initial condition. Question? This particular example was a first order differential equation because it involved the first derivative. But I can have second order differential equations and third order differential equations and fourth order and fifth. I can use as many derivatives as I want. But if I want a particular solution, I need as many initial conditions as the order. So if I have this derivative, f double prime of x is 12x squared plus 6x minus 4, and I want to get back to the original function, I need two initial conditions. Now, those two initial conditions can come in a variety of fashions. I could have one piece of information about f prime and one piece of information about f. Or I could have two pieces of information about f. That's the difference between initial conditions and boundary conditions most of the time. But I'm going to give you two different pieces of information. And they're both about f. But because I have a second derivative, I need two pieces of information. And so again, I want to do the same thing. I want to find the original function f of x that we got in this problem. So I take an antiderivative. But if I'm starting at f double prime, when I take the antiderivative, what function do I get? This is the second derivative of f. So if I take an antiderivative, I back up one step, I'm at f prime. Okay, what's the antiderivative of this? Believe it or not, this is all power rule. So let's start all the way on the left. What's the antiderivative of x squared? And the 12 just stays out front. What's the antiderivative of x? Well, that's x to the first. But this 4 doesn't have any x's with it at all. That makes it an x to the 0. Because x to the 0 is 1. Oh, okay, wait a minute. I can use the power rule now. What is the antiderivative for x to the 0? Notice I even wrote it the same way as x to the 1 over 1, but I could just write an x. But wait, there's more. I need that plus c. And now we can simplify these coefficients. 12 on 3 is 4. 6 on 2 is 3. I don't have to worry about that. There's my antiderivative. Am I in a position where I can use either of my initial conditions? No, because both of my initial conditions are about f, and this is f prime. So what do I need to do? Do it again. I need to take another antiderivative to get to f. Now, in the same way, I'm going to do the power rule again. So I'm going to get x to the 4th over 4, but there's a 4 out in front, so that's just going to give me an x to the 4th. I'm going to get an x to the 3 over 3, but there's a 3 out front. That's just going to give me an x cubed. 4x squared over 2, but 4 over 2 is 2. C. C is a number. What's its antiderivative? Exactly. Oh, forgot to write the squared. But wait, there's more. I already used C. I need to use a different letter this time to make sure I can tell these two things apart. So you could call it anything you want. You could call it C with a hat on it. You could call it C prime, whatever. But it's another different, potentially different number. I don't know what either number is. But now you'll notice I have two things I don't know. I don't know C and I don't know D. And I have two initial conditions up there. F of 0 and F of 1. Plug them in. If you plug in 0, you're going to get 1. Oh, sorry, you're going to get 4. F of 0 equals 4. So that's 0 to the 4th, 0 cubed, 2 times 0 squared, C times 0 plus D. What is the right-hand side expression?
D.
It's just D. Everything else is a 0, so D is 4. Which I can then use to figure out C. Because I have F of 1 is 1, so that's 1 to the 4th plus 1 cubed minus 2 times 1 squared plus C times 1 plus 4. And now I can figure out C. Because this whole right-hand side is 1 and 1 minus 2 plus C. This is C plus 4 equals 1. So C is -3. And now I have my particular solution. Ta-da! Questions?
Would we have to do final test, we have to do more than 2 derivatives?
If I'm being particularly vicious, maybe I'll give you 3, but that would be really sick, wouldn't it? On the other hand, if I'd given you information instead of 2 things about F, if I'd given you things about F and F prime, you could have used F prime to find C in the first place, up here, and then you would only have to find one thing here, right? Where is a case where you might actually only know something about the second derivative or the third derivative or something like that? Gravity is acceleration, isn't it? Acceleration is a second derivative. If I throw an object up into the air, its motion is an antiderivative. Because I know the acceleration it is undergoing. There is a wonderful example on page 300 and I think it's 78. No, it is 361. Example 7 here says you're going to throw a ball up in the air off the edge of a cliff at 432 feet up in the air. So you stick your hand over the edge of the cliff, you throw the ball straight up. It goes past the edge of the cliff and falls to the ground. 2 questions. How long does it take to hit the ground? How fast is it moving when it hits? I can picture this going up into the air and falling back down. One of your homework questions is based off of this example. Please read this example carefully. Monday is question and answer day for 4-7, 4-9, and the exam review. We'll see you all then. Have a wonderful rest of your day.